Okay. Sorry guys, like I didn't know that the class was there at 9:30. I'm really sorry for making the wait. Start right away. Anyways, good morning to all of you. All right. Okay.
Good morning, sir.
Good morning. Yeah. Good morning. Okay. So, one second, guys. I just closed the windows. I think there's some glare coming. Just give me a moment. Okay, fine. Cool. So we have to see today. I think it is metals or non-metals. Is it right?
Yes.
Yes, sir.
Okay, good. Right. Okay, so this is a very small chapter, right? So we know that it is going to start with what are the basic physical properties. Like say we know what are metals, right? We know what are non-metals, right? Basically, if you look at the periodic table, right? If I draw the periodic table, something like this. This is just a rough sketch, right? Okay, if this is the periodic table, you will see the left hand side, right? Basically, you have these two groups, right, are going to be metals, right? And eventually you'll see there are 5 blocks here, and they will generally be called as non-metals. Okay, right. So coming into the difference between non-metals and non-metals with respect to your physical properties, right? So what do you mean by physical properties? Physical properties are anything which I can see or feel physically. I can touch, I can smell, I can see, right? All this stuff, and whatever you are able to sense with your physical senses, right? Those are what are called as your physical properties, right? Okay, so physical properties, if I check, there are so many differences, right? Okay, so what is the first difference? Can you tell me between metals and non-metals? Physical properties.
Metallic luster.
Conduction.
Luster. Okay.
Conduction.
Conduction. Okay.
Hardness.
Sonorous. Okay.
Malleability, ductility.
Malleability, ductility, yeah. Right, ductility.
Melting points and boiling.
Melting points and boiling points. Anything else?
Physical state.
Density.
Okay, density. Physical state. Okay, good.
Hardness.
Okay, then. Sorry, hardness. Okay. Then. Okay, so yeah, these are all the so many differences you will see. Is there something wrong? Am I able to see the down part? Okay, cool. Right. So these are all the different difference in physical properties, right, between metals or non-metals. Say, for example, we'll speak about every one of them. Luster. What do you mean by luster?
The shiny.
Right. So yeah, shiny appearance, right? So shiny appearance, gold, silver, all these things will have very shiny appearance. But again, see, for everything there is definitely, we say that metals are generally lustrous, right? But again, you can have some exceptions, right? For every property you see here, right? For every physical property you see here, there will definitely be exceptions, right? You have to know what are all the exceptions also. Exception means, for example, certain non-metals will also be lustrous. Can you give me any examples? Non-metals.
Iodine.
Diamond, right? Is a very
diamond, iodine.
Iodine, yes, iodine gas. Yes, anything else? Okay, these two, right? So you have diamond, iodine, as you said. All these are non-metals, but still they are lustrous in nature, right? Okay, fine. Now when I go for conductivity, right? So metals are generally good conductors, good conductors of electricity, whereas non-metals are not, right? Okay, so now what you have to understand is, why is it that metals are good conductors? Can you tell me why metals are good conductors?
Because they have free ions.
Free electrons.
Right. So what you have to understand is, this metals will have free electrons present. So basically, when you want to pass electricity through a medium, right? Any medium for that matter, right? If you want to pass electricity, you have electricity chapter in your 10th class, right? So if you want to pass electricity to through a medium, right? So that medium should have some free charge carriers. Charge we know, positive charge, negative charge we know. So there should be something which should be able to move through the material, move through in the sense there should be the what to say, the particles which are there in the medium should have some charge, first point, right? And that charge should be able to move through the conductor, move through the material. Only then I call them as conductors, right? So as you said, metals will have free electrons, right? Metals will have free electrons. I know electrons are negatively charged, and this if electron moves through the medium, that becomes a conductor, right? So again, generally metals are good conductors of electricity, or as well as heat, right? They are conductors of heat as well as electricity, right? So again, there might be exceptions, right? So can you give me any non-metal which will be a good conductor of electricity? Graphite, right? Again, carbon's allotrope, graphite, right, will be a very good example for a non-metal being a good conductor, right? Okay, fine. Next, about sonorous. What do you mean by sonorous?
It gives sound, sir.
It gives
The
sound,
sound
just
while
like
produced when hitting.
correct. So when you hit that particular material with some hammer or some kind of tool, it is going to produce sound, right? So we know, right? Aluminium sheets, iron as a metal. So you have seen so many places where they do it, right? When you're welding things, right? When you want to make, say, when you want to build a building, right? So what they do is they cut, they strike it with some hammer or something, so it produces sound, right? Fine. But not all metals are sonorous. Can you give me any example of metal being non-sonorous?
Lithium, sodium, potassium.
Lithium, sodium, potassium, all these are soft metals,
Potassium.
right? Yeah,
They
lithium.
can be cut with.
Correct. Though that comes in hardness also. Generally, metals are hard, right? So, but these potassium, lithium, and sodium, all these can be cut with knife. They are very soft metals, right? So that is again an exception. Okay, cool. Next, about malleability. What is malleability?
It can be
It
beaten
can
into
be
sheet.
beaten into thin sheets.
Right. So you have to properly say
Example,
the
aluminium.
ability of the element or ability of the species to be drawn into sheets. Right. So you can have aluminium sheets, you can have tin sheets. Tin is also a metal. Tin, you know, SN is the symbol for tin. Right. So that is also a metal. Right. So all these aluminium sheets, tin sheets, iron sheets, right, or asbestos is again an alloy of all the metals. So all these things will be able to draw them in the form of sheets, copper sheets. You must have seen in pujas and all they use the copper square, right? That's very auspicious in Hindu mythology, right? So all these things can be drawn into sheets. Okay. Again, there can be exceptions. Again, sodium, potassium, lithium is again an exception here because they cannot be brought into sheets because again they are very soft metals.
Cesium and gallium.
Yeah, like all the group 1 elements. So you see the group 1, this is the entire group 1: lithium, sodium, potassium, rubidium, cesium. All these things belong to the same family of elements, same family of metals, group 1 elements, right? So all of these will generally be non-malleable. Even calcium again cannot be brought into sheets, right? Okay, fine. Next is about ductility. What do you mean by ductility?
Ability
Ability where
Thin
to
wire.
be drawn in
Wires.
wires.
Correct, right? Everybody is correct, right? So that is the ability of the material or ability of the element to be drawn in the form of wires, right? So you must have seen so many, right? We use generally copper wires for our buildings, for our homes, right? Now, if at all you want higher efficiency, like, but it's a little costly. If at all you use gold or silver wires for all your wiring purposes, in electricity purposes, they will actually be more efficient. But we know why are we not using it? We are not using it because of economic or financial constraints. Gold or silver wire will always be very costly compared to copper wires. Even aluminium wires can be used, but aluminium wires are little less efficient when compared to copper wires, right? So again, there can be exceptions here, right? So there can be again sodium, potassium, lithium, so all these group 1 elements again cannot be drawn into wires. Okay, that's an exception. Okay, cool. Next, boiling point, melting point. Which will have higher boiling point, melting point?
Metal.
Metals, right? Generally, metals will have higher boiling point or melting point. Again, it's because what you have to understand is in chemistry, right? There can be three types of bonds. Okay, what do you mean by a bond? A bond is something like an interaction. Say, for example, I have AB as a molecule, right? So you see this dash I put here represents some kind of attractive force, right? Some kind of attractive force. So we have different types of bonds in chemistry. Say I have something called as ionic bonds, right? I have something called as covalent bonds, right? And third type of chemical bond is what is called as your metallic bond. Right, I think this, I don't know whether you have learned, you would have heard this term, right? So metallic bond exists between two metals. I mean, two metals means atoms of two metal, between one copper atom, another copper atom, one sodium atom, another sodium atom. So basically, if I take a say if I take a sheet of metal, right, there will be millions and millions of atoms in that, right? We know atoms are very small, so you will have so many millions and billions of atoms present, right? How are all these atoms able to be together is the question, right? So they are existing together. All these atoms exist together in a kernel, in a structure, right, with the help of these kind of metallic bonds. Okay, so metallic bonds are very strong bonds. Okay, like if I generally say ionic bonds are the strongest, ionic bonds, you know, sodium chloride, if I take sodium plus Cl minus, so a cation, anion, electrostatic force of attraction. We know positive charge attracts the negative charge. Unlike charges attract each other, right? So like that, ionic bond is one of the strongest bonds, right? Then comes metallic bond. Metallic bond is the second strongest bond. Then comes your covalent bond. Covalent bonds are the weakest in chemical bonds. Okay, right. So because they have very high bond energy, right? Because these metallic bonds are very, very strong, right? That is why we have to supply more temperature, more amount of energy, right, for them to go into gaseous phase. For example, if I have a liquid metal, can you give me any example for liquid metal?
Mercury.
Mercury. Any other thing?
Mercury.
Anyone? Anything else other than mercury?
Do gallium and cesium count?
Cesium, no. Gallium, yes. Right. Gallium is a very good example. Right.
Gallium.
So gallium, if you take gallium, will actually, if at all, if you're gonna have say temperature like around 20 degrees Celsius, which is less than room temperature.
Melt and room.
Yeah. So if it is lesser than room temperature, it will be solid, right? But the moment you take it out of the box and you keep it in your hand, it will start melting because it has very less melting point. So that is again an exception, right? So generally metals will have higher boiling point or melting point, but I have some liquid metals itself. Examples can be mercury and gallium. So that is an exception for boiling point and melting point. So what I'm trying to say is because of these very strong metallic bonds, right, which exist between the metals, they are easily going to go to, I mean, it is very tough for them to go to the gaseous phase because the bonds are very strong to each other, very closely attached with each other. That is why you have to supply more energy or say more temperature for it to go to the liquid phase or gaseous phase, whatever. Okay, but in case of gases or in case of non-metals generally, now when you go to the physical state, right? Physical state, generally we know that metals will be in solid state generally, but again I can have liquid metals as you told. Gaseous metals, no, right? Generally metals will, you can make the metal go to gaseous phase, but normally how they exist in nature, they exist only as solids or majority solids, very few liquids, right? But if I go for non-metals will generally be gases. Is it not? Oxygen gas, nitrogen gas, chlorine gas, fluorine gas, everything, whatever you see generally will be a gas. Again, I can have exceptions in non-metals being solid. Any examples?
Carbon.
Yes, carbon. You see carbon in nature, coal or graphite or diamond or whatever fossil fuels you see. Petroleum is not only carbon, it is carbon plus hydrogen. But anyways, right, you generally see carbon in liquid state, or some majority you will see carbon in solid state. Any other non-metal, you know, which will be in solid state?
Plastic.
Plastic is not an element. No? Plastic is a combination of elements. What is it?
Iodine.
Iodine will be a gas generally. Iodine will be a brown colored gas.
Then how can that be shiny? I mean, how can that have luster?
Exactly, that's a good question. So what happens is I will be able to easily compress iodine gas into iodine solid. So that iodine solid will have luster, this thing. But in nature, at room temperature, at normal conditions, you see iodine. Iodine is now, if at all now you see iodine in your room, it will actually be in the gaseous form, right? But if you control the temperature, if you control the pressure, then I will be able to go to the solid phase. There you will have luster. Understood?
Yes, sir.
Okay, right. So what I was talking about any other non-metal being in solid state other than carbon, right? So one good example is phosphorus, right? Phosphorus is a very good example. Phosphorus will generally be a non-metal. It belongs to nitrogen family. If you see nitrogen will be here, and next to nitrogen you will have phosphorus in the periodic table. It's a non-metal, right? Okay, so where can you see phosphorus? Can you tell me where can you see phosphorus? We are actually using it in our real life so many times. Where do we use it? Do you know?
Fertilizer.
Fertilizer or phosphates. It's not only phosphorus. Phosphates are PO4 3-
Phosphate
ions.
is present in our teeth.
Sorry. Exactly. That is phosphate. In our teeth, calcium phosphate is present. Right? In our bones, calcium phosphate is present. Those are phosphates. Those are ions. I'm talking about phosphorus, P only. Where do we use it in our real life? Okay. You must have seen some magic tricks, right? In magic tricks, what they do is they do like this, and I'll get fire here. I don't know. There is a famous comedy also, Thipuri Tirumugam. Have you watched it? Have you watched the comedy scenes?
Yes, sir.
Right. So there, it's basically a magic trick. If they do like this, fire will come. Right. So basically, that is phosphorus. So what they do is in between the nails, right? So this white, there are actually different types of phosphorus. I have white phosphorus, I have red phosphorus, I have black phosphorus. Different colors of phosphorus are available. Okay. So what I've done is it's in solid form, right? So what they do is in between the nails, they fill with phosphorus, and this phosphorus is highly inflammable, right? It will easily catch fire. Okay, so but they'll be closing it like this, but the moment they do like this, it is exposed to air and it will catch fire, right? So that is the trick. That is the beauty behind the magic trick. It's basically chemistry, right? Okay, and you see matchbox, right? In the matchstick, at the end you see that red color or black color thing which is coming. That is again a phosphorus. That is red phosphorus. Or if you see a black color thing coming up, black color thing which is red, it is black phosphorus. So basically, what you have to understand is phosphorus is highly inflammable. It will easily catch fire, right? So that is the reason why we use it in matchsticks. Okay, so again, that is a exception. Non-metal being a solid. Phosphorus is again a very good example.
So in matchsticks, it's white phosphorus.
White? No. White phosphorus will be white in color, right? So how you have carbon to have allotropes, right? I have graphene, graphite, I have Buckminster fullerenes, I have diamond. Like these, phosphorus also has some allotropes, right? What do you mean by an allotrope? Allotrope is basically same element existing in different forms in nature, right? So how you have different allotropes of carbon, like that you have different allotropes of phosphorus also, right? So you have three things: white, black, and red, right? So in matchsticks, we use only black or red. Why we use only black or red is because white phosphorus is very highly inflammable. So the thing is, only if you scratch it, the fire should come in case of a matchbox. If it was white phosphorus, just to show it to the atmosphere, it is going to catch fire. That is why we don't use white phosphorus. We use only black phosphorus or red phosphorus, which is a little less reactive when compared to white phosphorus. Okay, right? Good. So that is about the physical state. Again, density coming, all these can be put together in one thing. Density, again, metals are generally having high density because they are solids, right? And generally non-metals are gases which are going to have less density, that we know, right? So these are all the different differences in physical properties of metals and non-metals. Okay, right, cool. Now, if I now go into the chemical picture, right, when I say chemical properties, right, so when I say chemical properties, we talk about how that particular species interact with other chemical species. Okay, I have a molecule A. If I bring that molecule A near a molecule B, how are they going to interact? What are the different things are going to happen? Those what are called as chemical properties, right? Physical property is what we see, what we feel by our senses, right? So chemical properties are the one which is because of the interaction between two molecules or two atoms or two elements or whatever it is. Okay, right? So that if you look into it, we'll see what's going to happen. Right. So if I look into the chemical properties, right? So first and foremost thing, right? So we say generally metals are electropositive in nature.
Positive.
Right? They are electropositive in nature. What do you mean by being electropositive?
They give electrons, donate electrons,
Correct.
electron donors.
Correct. Right. So basically, metals have good tendency to lose electrons. Right? Metals have good tendency to lose electrons. So when I say positive, that means they are capable of forming positive ions. That means cations. Does it matter? Right? Metals are generally capable of forming positive ions. That is why they are called electropositive elements. Right? Okay. So now I know positive ions are what are called as cations. Now, how do you form a positive ion or a cation? Obviously, by losing electron. Right? So either you can say electropositivity means ability to form a positive charge or a cation, or you can say that it is the ability of the element to lose electron. Either way, you're going to end up with the same thing. That is, you're going to form the cation. Okay, so that is why you see, if at all I'm going to have an interaction between a metal and a non-metal, say for example sodium and chlorine, sodium always form the positive charge because it's a metal. And if I go to non-metals, you see they are going to be highly electronegative in nature. Non-metals are electronegative. That means what? They can easily form negative ions. Negative ions are what are called as anions. Right? How do you form an anion? Obviously by accepting electrons.
By gaining electrons.
Correct. Right? They're gonna gain electrons. Right? So this we know. So all entire difference in chemical property. Why is it that metals and non-metals behave, react differently with different substances? The main reason is these two. Metals are highly electropositive, whereas non-metals are highly electronegative. Metals are going to form positive charges cations. Non-metals are going to form negative charges anion by gaining electron and by accepting electron and by gaining electron respectively. Okay, right, good. So this we understood. Now we can go for some reactions. Right? There's the time. Okay, fine. We have time. Cool. Say first, I'll speak first about metals. Right. Okay. Say first with water. Okay. Metals with water. Right. So what is going to happen generally? Yeah. Tell me, what is it?
Metal oxide plus hydrogen.
Plus hydrogen.
Yeah. That is general. Right. That is in general. Okay. Fine. Actually, different metals are going to form different kind of products when they're exposed with water. Right? Say for example, if I take highly, I'll change the marker once. So if I have highly, this is better, right? When I have highly reactive metals, right? What are highly reactive metals? Can you give me some examples?
Sodium, potassium.
Sodium, potassium, then
Phosphorus.
Lithium.
Phosphorus is a non-metal. Okay, lithium, calcium.
Magnesium,
Okay,
magnesium.
magnesium will not take it into here. Magnesium will be little, I would say, medium reactive element, not highly reactive. Okay, Right. So lithium, sodium, potassium, calcium, all these are highly reactive elements. Right. So I don't know, you didn't go to school. If you would have gone to school this year, right, you would have done an experiment. You would have done a chemistry experiment. What you would have done is you would have taken a piece of sodium, right, and you would have put it in a vessel containing water. Okay. Did you do that experiment in somewhere? Did you? I really don't think so. Did you go to school and do this experiment? No, right?
No.
No,
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 sir.
sir.
Right. So maybe you will see it when you go to school. When you go to the chemistry lab next time, when you go to school, ask your teacher to show it. Okay, how vigorously you see that sodium
Flame
reacts
will be
with water. Sorry, what is it?
fire will be produced immediately.
Correct. It is a very vigorous reaction, right? But the moment you put sodium, it will just bounce and so much reaction will happen, right? So same goes with calcium, not so much, but it is really highly reactive. Potassium is still more reactive than sodium, right? Okay, so generally what you see, if these metals are there, I just put it as M, any of these four metals M with water, they are going to form hydroxides, right? Or if I put, for example, sodium will form sodium hydroxide and liberates hydrogen gas. Same goes with all the four elements. Potassium will form potassium hydroxide. Calcium will form CaOH twice, plus hydrogen gas will be evolved. Right. Okay. Now tell me, how will you prove that hydrogen gas is getting evolved?
Bring a burning
By placing
burning
burning
Burning. Okay. Wait.
pop sound.
Okay, fine. So when I bring a burning matchstick, that burning matchstick will be put off with a pop sound. Correct. So these are the type of questions will be coming in your exams. Okay, how will you prove that H2 is getting liberated? How will you prove that CO2 is getting liberated? Then you have to tell lime water turning milky, that reaction. I think that we saw in your first chapter itself, right? Lime water, CO2. If I pass through slaked lime, you're going to form calcium carbonate and calcium carbonate and CaCO3 is going to get, CO2. CaCO3 is going to get formed. That is what is forming the milky solution, lime water turning milky. That is how you prove CO2's evolved. If CO2 is evolved, that is how you prove it. Okay, right. So these are highly reactive metals, right? They will form hydroxide. Remember this. Okay. Now, when I have intermediately reactive elements, intermediate reactive, right? So here I can have magnesium, aluminium, iron, all these things can be examples. These are moderately reactive elements. Okay, so moderately reactive elements will generally, so what you have to understand is here, this water, once again, right? This water you use will generally be, even if it is cold water, the reaction will happen, right? But for them to react, for these to react, right, you must either have very hot water, right, or you need to have
steam.
good, right, or you need to have steam, right? So steam is also generally H2O only, but in gaseous phase. Correct, right? So here if I just put, say, for example, magnesium, and if I react with its steam, right, now here it is going to form magnesium oxide plus hydrogen. Okay, right? So this you have to know. So highly reactive metals will form hydroxides, lesser reactive metals will form oxides. Okay, that is the difference that you have to know. And why this happens is because of difference in reactivity. Okay, so we'll speak about it. Why is it that there is a difference in reactivity? That we'll speak. For now, you know that these four are highly reactive. They'll form hydroxide, and intermediately reactive metals, like moderately reactive metals, will react only with hot water or steam. They will not form hydroxide, but they will form oxides. Magnesium oxide, aluminium oxide, iron oxide. All these things will be formed. Okay, now there are certain metals which will not react with H2O. What are those elements?
Gold, silver,
Gold,
right,
copper,
correct,
lead,
right, which will not
lithium.
react with copper, gold, silver. All these things are not going to react with water. Okay, why? It's because of, again, reactivity. Now you have to know, like, if you have to understand this, we already spoke about reactivity series right? It depends, all this depends on reactivity series. Okay, reactivity series, say for example, sodium, potassium, calcium, lithium, magnesium, aluminum, iron, then comes hydrogen. Okay, after all these elements, after iron, you see hydrogen. Hydrogen can behave as a metal as well as a non-metal. That's a very anomaly, isn't it? That you have studied in periodic table also. Hydrogen can be placed in group 1 or it can be placed in group
Group
it can be
17.
correct, right? Yeah, good, right? They can be either placed in group 1 alkali metals, or they can be put in group 17, that is halogens, right? Okay, so after hydrogen, right, after hydrogen only you have copper, gold, silver, all these things come. So what you have to understand is, here basically you see it is hydrogen oxide, is it not? So you are trying to replace this hydrogen with a metal here, correct? So this reaction will happen only and only if the metal is more reactive than hydrogen, is it not? But you see, if you use copper, gold or silver, you see they are less reactive than hydrogen, so they will not be able to replace hydrogen from water, right? So that is why they don't react with water. And same reason is the same reason why these metals won't react with acids also. Acid also contains H plus, isn't it? So they will not be able to react with acids. So, right? Okay. Now, when I take non-metals, guys, if I take non-metals, right? If I put a non-metal, I just write an NM. If I put H2O, what will happen? Any idea what will happen? Nothing will happen. No reaction will happen. For example, N2 you have, nitrogen gas you have, carbon you have, right? Oxygen gas you have. Anything you take, any non-metal you take, right? Any non-metal, if you're going to react with water, there is no reaction. Okay, right? So again, there is a difference between that. Metals will react with water to form hydroxides or oxides, depending on which metal it is. But non-metals are not going to react with water. Okay, right. Fine. So that's about reacting with water. Any questions? Okay, fine. Then we'll move on. Then we'll see action.
Sir,
Yeah.
I actually do have a question, but it's not exactly related to this topic.
No
So
problem.
there are some questions from chapter 5. So they would give us this periodic table and a few elements in it. And one of the question will be like, which has the biggest atomic radius, which is more electronegative, and they'll ask which is more reactive. So what should we write to? I mean, how does that relate to this?
Okay, fine. So we will discuss more about this when we go to periodic table, but since you asked that question now, I'll tell you, right? So we know in periodic table we have groups and periods, right? The vertical things are what are called as groups, the horizontal rows are what are called as periods, right? Okay, so now what you have to understand is, if you can understand how electropositivity and electronegativity changes across, down the group and along the period, then you will be able to easily predict the reactivity. Okay, right. So please understand first, when I go for electropositivity, right? So electropositivity increases down the group.
Down the group.
Right? When for example, if I compare lithium, sodium, potassium, potassium is more electropositive than sodium. Sodium is more electropositive than lithium. This is one way of looking at it. Right? Now, when I go from left to right of the period,
It decreases.
right? It decreases. Okay, that is why you see sodium is more reactive than magnesium. Magnesium is less reactive. Right?
Due to increase in nuclear.
Yeah, due to decrease. The reasons are there. I'll come to the reasons why this increases, why there's a decrease and all. I'll tell you. But for now, just know this, right? So along down the group, electropositivity increases, and along the period, from left to right of the period, electropositivity decreases. Right? It is going to be exactly opposite for electronegativity. Down the group decreases, along the period increases. What you saw here exactly ulta for electronegativity. Okay, so reactivity, if I speak, reactivity of metals is directly proportional to its electropositivity. Same way, reactivity of non-metals is directly proportional to its electronegativity. Okay, so this, if you can understand, then you will be able to easily say which is more reactive, which is less reactive. And what is the reason for this is the next question, right? Why is it that when I go down the group, the electropositivity increases, or say when I go along the period, the electropositivity decreases? Is that question you have to answer? Any answers?
Can I say?
Yeah, sure. Yeah.
Since the number of shells increases, the ability of the nucleus to hold electron decreases.
Good. Yes, that's the reason.
That's why it loses electron easily when we go down.
Absolutely true. Right. So why now when I go down the group, what is happening to the atomic size? You're adding more and more number of shells when I go down the group. Say for example, lithium will have 2,1, sodium will have 2,8,1, potassium will have 2,8,8,1. Right. So when I go down the group, you see the number of shells are increasing. So basically the atomic size is becoming bigger and bigger and bigger. Right. Okay. So because of that, what is going to happen? What is electropositivity? Electropositivity, that's how I told you, it is the ability to lose electron, or it is the ability to form a positive charge. Right. So if I talk in terms of ability to lose electrons, right? So obviously when the valence electron, the last shell, if it is very far away from the nucleus, right? If it is very far away from the nucleus, I know nucleus is positively charged, right? So this nucleus and the electron in the valence shell will have some attractive force, right? So now what you have to understand is, if the force is little less, then I can easily remove the electron. But if the force is very strong, right, removal of this electron is difficult. Right. Now, how this force will vary? Obviously, this force is going to vary depending on the distance between the nucleus and the electron. Right. So if the nucleus and the electron are very far away from each other, right, obviously the force would be less. Right. But they were very close to each other, then they'll have very strong interaction. Removal of this electron is difficult. Right.
Yes.
Okay. So when I go down the group, the size increases, the distance between the nucleus and the electron increases, so thereby you can easily remove the electron, right? So that is why you see when I go down the group, the electropositivity, or say the ability to lose electron, increases, right? Okay, now when I go along the period, same reason. When I go along the period, atomic size decreases. Why? Because in the same shell, say for example 2,1, 2,2, 2,3, 2,4, 2,5, like that it will go in the period, right? So in the same shell, you are adding more and more number of electrons. So obviously, if you add more number of electrons in the same distance in the nucleus, obviously the force will be very strong, right? So that's why the atomic size decreases and the ability to lose electron also decreases. Okay. So like this, you will be able to answer. We'll see in depth when we go for periodicity. Okay, sure, we'll discuss all the stuff. Don't worry. Okay, good. Fine. So now we'll see what happens if metals and non-metals react with acids, right? Okay. So what you have to understand is metal plus an acid will form
salt plus hydrogen.
Right. It is going to form salt plus hydrogen gas is going to get evolved. Right. Now, what type of salt depends on what type of acid we use, depending on what type of anion is present in the acid. For example, if I put magnesium with HCl, you are going to form MgCl2. The anion is here. Again, hydrogen will come, obviously. Right. Or say if I put calcium with H2SO4, now you see the anion is sulfate anion. Right. So in this case, you will form CaSO4 plus H2. Again, a displacement reaction. Exactly. Right. It is like a displacement reaction. The metal is replacing hydrogen from its acid. Okay. But again, as I told you, certain metals will not react with acids. Copper, gold and silver will not react with acid because they are less reactive than hydrogen. right? So these things you have to know. And what happens if I have a non-metal, like say carbon, reacting with HNO3? What will happen?
Won't react.
Nothing will happen. Exactly. Non-metals do not react with acids. Okay, metals will only react with acids. Okay, fine, good. Next. Okay, so next thing is action with, say, hydrogen, H2 gas. Again, you can see, so that's a non-metal. Yes, it is a non-metal, but hydrogen gas, oxygen gas, all these are abundantly available in the universe, right? So obviously we have to understand how metal or non-metal reacts with oxygen. Like even though we categorize oxygen as a non-metal, right? Certain non-metals itself will react with oxygen. Certain metals will react with oxygen. So all these things will happen, right? It's very simple to understand. Any element, right? Any element, whether metal or non-metal, metal or non-metal with oxygen is going to form oxide. Any metal or non-metal will react with oxygen. Basically, up to reacting with oxygen is what is called as reaction with oxygen is what is called as
Oxidation.
other way. If I'm going to bring in heat and all,
Reducing of hydrogen.
no. If I say something is burning with oxygen, what is the term I use?
Exothermic reaction.
Endothermic.
Exothermic reaction.
No, what I'm expecting is different.
Decomposition.
No,
Combination reaction.
no. Combustion, right? What is combustion? Combustion means burning with oxygen. Okay, so all these reactions are combustion reactions. Right? You must have heard this term. Right, combustion reactions. Right, combustion means burning with oxygen. All these, whatever you told are correct. It's oxidation, it is endothermic, all these are right. But what is the perfect word? Perfect word is combustion. Combustion means burning with oxygen. Okay, so anyways, right. So for example, we'll say some examples now. Right, say for example, if I have magnesium, or I'll take some other element. I'll say calcium. Calcium also I took, say sodium, reacting with O2 to form Na2O. Right, this is a metal. Right, if I take a non-metal, say I take phosphorus as a non-metal, or I take nitrogen plus O2, will form so many types of oxides of nitrogen are possible. You have NO2, N2O, N2O3, N2O5. All these things are possible. You don't have to worry about it. Okay, write any of the oxide, doesn't matter. Okay, whatever you remember, that you write. Whatever the type of oxide you remember. Same with phosphorus, you can will form two things. One is P2O3, the other one is P2O5, phosphorus trioxide and phosphorus pentoxide. Pent, I know, is 5. Right, trioxide, pentoxide. So two types of oxides are possible for phosphorus. So you see, metals are also forming oxides, non-metals are also forming oxides. Okay, so that's about. Oh, I said. Oh, sorry, I'm really sorry. I said hydrogen. This is O2. Okay, so reaction with O2 is what we are seeing. Okay, right, fine. Moving on. I have, say, next one is action with hydrogen. If I take, right, fine. So remember that metals plus hydrogen will form metal plus hydrogen will form
Metal hydrides.
good, right? They will form metal hydrides. Okay, right. So it's very simple, right? What you have to understand is hydride is basically H minus ion. It's that's the reason why I told you hydrogen can be put in halogen family or it can be put in alkali family, because it is capable of forming H plus, like Na plus, K plus, Li plus, or it can form H minus, like Cl minus, F minus, Br minus, I minus. Like that's the reason why I'm able to put it everywhere. Fine. Either in group 1 or group 17. Right. Okay. So what you have to understand is the metal which is here should be more electropositive than hydrogen to react here, than hydrogen. Only then they'll form the metal hydride. Okay, say for example, sodium will react with hydrogen to form sodium hydride, NaH. Calcium will form calcium hydride, right? But not all elements, not all metals are capable of forming hydride. But for example, if I take aluminium capable, but not so much. It's all big depends on the reactivity. Highly reactive elements will easily form the hydrides, but less reactive metals, you have to supply more energy, more amount of temperature, more pressure for them to form the hydrides. Okay, right, fine. Now when I go to non-metals reacting with hydrogen, right? Now what you have to understand is non-metals are actually more electronegative than hydrogen. They're not electropositive. Right. So here you see they are forming H minus, but there you will see hydrogen will be in the form of H plus. Why? Because they are more electronegative. Non-metals are more electronegative means what? They are having more capability to form the negative ion than hydrogen. But in this case, hydrogen is more electronegative than the metal, right? So that forms the anion. Okay. Right. So if we cannot call them as, obviously I just call them as products, right? I cannot call them as any specific name, right? But depending on the compound, I can give some names. For example, if I write N2 plus H2 giving ammonia, this is a very famous reaction, right? N2 plus 3H2 gives 2 ammonia. Habers process. You would have heard it. Have you heard this term, Habers process?
No, sir.
Okay, so please understand, this is an industrially very important process. This is how you produce ammonia in industries, right? It's called Habers process. Okay, N2 reacting with H2 to form ammonia. NH3 is ammonia, right? So again, you have to use Fe as a catalyst, some 600 degrees Celsius, all these things, very high temperature, very high pressure, and all these things you have to use. You don't have to worry about the details here. So what you have to understand is N2 plus H2 is going to give you ammonia. And one more example I can give you is like carbon plus hydrogen will form methane, right? So these kind of reactions are also possible. It's not like non-metals will not react with hydrogen. They will react with hydrogen to form their own compounds. Okay, right? Fine. So that is about reaction with H2, right? Okay. What are the stuff? Okay. Now we can see we talk about metals, right? We can talk about metal oxides and non-metal oxides. How are they different? How are they chemically different? That also we'll be able to see. Okay. So we are going to study about metallic or non-metallic oxides. Okay, how are they chemically different? Right. So what you have to understand is your metallic oxides.
Basic in nature.
Yes, absolutely. Right.
Basic.
They are basic in nature. That means their pH will be greater than 7. Okay, and exactly opposite in the case of your what is that? Non-metals, which are acidic in nature. Right? They're going to have pH lesser than 7, non-metallic oxides. How do we prove it is the next question. Prove it, you can use the help of a pH. Definitely, if you measure the pH, those solutions will generally be having pH greater than 7, metallic oxides. Other than that, how will you prove? You go for, say, for example, if you take a metal oxide, any metal, there's a problem with the marker. Second, guys. Okay, I have to buy new markers. I have been telling it for a long time. So when I have a metal oxide reacting with water, what will happen? Yeah, right. They will form metal hydroxides. For example, if you have Na2O reacting with H2O, you will form NaOH. Right? They'll form NaOH. Now you see where the aqueous solutions, if I have a salt, sodium oxide will be a salt generally, right? So that salt you dissolve in water. By the moment you dissolve in water, you are actually going to produce a base, right? So that is the reason why we say that metallic oxides are what is that? They are basic in nature. They're going because they're going to form bases in their aqueous solutions. What is the other way of proving it? The other way of proving it is by, if at all they are basic in nature, right? They should undergo neutralization reaction. With the, say for this, if these are basic in nature, if I add an acid, right, they should form salt and water. Correct. That is what is neutralization reaction. And they do this, right? Say, for example, if you have Na2O, for example, if you react with HCl acid, they're actually going to form salt and water. Very simple. NaCl plus H2O is going to get formed. Obviously, you have to balance the reaction, guys. Don't forget it. You have to balance all the reactions. Okay, so you see Na2O reacting with HCl. This is a base reacting with acid to form salt and water. Right? So these two reactions which you saw now prove that metallic oxides are basic in nature. Right? Okay, fine. Now, when I go for non-metallic oxides, exactly same way we'll be able to prove it. Right? Okay, so we know every marker sucks. I'm sorry, so sorry guys if you're not able to see properly. Right, so I have non-metallic oxides will generally be acidic in nature. Okay, now how do I prove it? Like the same thing. For example, if you have a non-metallic oxide, say for example, if you have NO2, nitrous oxide, right? So NO2, if I react with water, right, what is it going to form? It is going to form nitric acid, HNO3. Right? So last time what you saw, when I have a non-metallic oxide, if you have a metallic oxide reacting with water, it forms a base. Right? So here you see a non-metallic oxide reacting with water to form an acid. The same way I'll be able to say another reaction also. For example, if you say I have SO3, SO3 reacting with water is going to form H2SO4. Right? Say if I have CO2 reacting with water to form H2CO3. Right? Now these two reactions are very important. Why they're very important? Can you tell me? Important not with respect to your marks, with respect to knowledge. Why is it important?
We produce highly reactive acid.
No. Something related to some environmental condition. Another example, another clue you want? Taj Mahal?
Acid rain.
Acid rain.
Right. So these two are the reactions which are responsible for acid rain. You have carbon dioxide in the atmosphere. You have water molecules in the atmosphere. So if you have very high concentrations of CO2 present, they will react with water to form carbonic acid. Right? Now this carbonic acid is the main component of your acid rain. Right? So it's not only water reacting with carbon dioxide to form this will be the one which will be falling on your Taj Mahal, which is actually degrading those structures. Okay, same goes with SO3. Sulfur trioxide again is a pollutant. When you use vehicles and all, SO3 will also get emitted. Right? So SO3 again reacting with H2O to form H2SO4 or H2SO3. A sulfurous acid that is also there, but again, don't worry about the details. What you have to understand, this is the main reason behind acid rain. Okay, cool. So you see that they're able to form acids when they react with water, right? Okay, cool. That is about. Okay, now if at all I have to prove them with via a neutralization reaction, I'll be able to prove it also. Say if I have SO3 reacting with NaOH. Now this is an acid, This is going to react as a base. So you are going to form Na2SO4 plus H2O. Again, you see the reaction is happening. Acid plus base reaction. Acid plus base gives salt plus water. That reaction is happening. Correct? Right? So all these reactions prove that non-metallic oxides are acidic in nature. Okay, right? So is there anything left in this chapter, guys? Did I miss anything?
How are the metals react? How do they react with nitric acid, sir?
Same thing, right?
Like,
If I have understood what your question is. It's pretty simple, right? Sorry, what did I tell you?
No, in textbook they just told us which metals react with nitric acid and which don't. But there was a question in my exam which said hydrogen gas is not evolved when nitric acid reacts with metals, except for magnesium and manganese give
manganese.
these.
Okay. Now what you have to understand is,
the
guys.
reason-
Yeah, understood. Now the thing is, HNO3 is a very special acid. Okay. HNO3, why is it a special acid? Is because it's a very
It's a strong oxidizing agent.
Yeah, exactly. Right? It's a very strong oxidizing agent. Okay. So what do we expect is, for example, if I put sodium, right, if I put HNO3, what we expect is NaNO3 plus H2. This is what we expect. Okay, but what is going to happen is this H2 is not going to get evolved because this HNO3 will oxidize H2 to H2O. Right? Basically, NaNO3 aqueous solution is what you're going to form. Hope you understand. NaNO3 with water basically is what? The salt solution. NaNO3 is a salt in water is going to form salt solution. Why hydrogen is not getting evolved? Because HNO3 is a very strong oxidizing agent. It will oxidize H2 to form H2. That's the reason why is it like this. Right? Now, why only magnesium? Right? Magnesium reacts with HNO3 to form MgNO3 twice plus hydrogen. Okay. Now, why this reaction happens and not the others is a very good question. Anybody wants to comment? Why any guesses of why this is going to happen? Why not the other metals?
Is it because
Okay.
it's
Is it because?
magnesium is more reactive compared to sodium?
No,
Sorry,
we know
sodium is more.
Magnesium.
Correct. That's the reason. Right. Magnesium is little less reactive. The reaction is little slow. Right. But this is very spontaneous. The moment you add a drop of HNO3 on sodium, this reaction is going to happen. Right. And in that moment itself, hydrogen gas will be evolved and that will be oxidized to H2O. But here, the reaction is little slower. Right. So slowly, only hydrogen will get evolved. So the HNO3 will not have time to oxidize H2 to H2O. So hydrogen gas will be evolved because it's a gas, isn't it? If it's very slow, the gas will be coming on until it will escape. Right? But here, during the reaction happening itself, this H2 is going to get oxidized. Okay, that's the reason here. Okay, that's a very good question. Right, good. Okay, so anything else like this? I think I've completed everything, whatever the reactions, whatever the physical properties, whatever stuff, I think I've completed it. Is there any other question?
Sir,
yeah.
Can you tell me how to form the product, sir, by giving two reactants?
Okay. It's simple. It depends on the reaction. If it's a displacement reaction, it's very easy. Okay. If it's displacement, like say anything, I have aluminium reacting with say H2SO4. Now, what you have to understand is aluminium is going to replace hydrogen. Correct, right? Yes, so this is a sulfate anion, right? So in the salt, you are basically going to form aluminium sulfate. Right, I told you in the first class, how do you write the formulas, right? Al3 plus SO4 2 minus. How do you write the formula? That is very easy, right? So mostly for your level, right, you will either have a displacement reaction or you will have double displacement reactions, right? Now double displacement, you know, right? You have to exchange both the cations and the anion. That's it, very simple. So if you know which is going to get replaced, right? The only problem you'll find is writing the formula. And I told you how to write the formula. I gave you a trick, right? You remember what all the anions, you remember what are all the cations, and you exchange the charges, you will eventually end up with a product.
Sir, for example, Fe plus H2Os.
Fe plus H2O. Okay, those kind of reactions are little exceptions. Okay, so generally what I expect is metal reacting with water to form hydroxide, right? But that's actually an exception. Exception is you're going to form oxide. So those kind of stuff you have to remember, guys. There is no trick to, or say there is no logical explanation, because that is how nature works, right? You cannot ask why sun rises only in the east, because that is how nature works, right? So certain things we have to remember. There's no other go. But most of the other chemical reactions, there is logic behind it. You don't have to mug it up, right? Okay,
Yes, sir.
right, cool. Any other questions? What is the time? Yeah, time is 10:40. I started by 9:40, so we'll finish it. Any other question, people? So I think next class we'll take periodic table. Okay, next class will be next week, right? So we'll take a periodic table. That's a very interesting chapter, right? Fine. Any other questions?
Sir, you said how to prove the metal oxide is acidic or basic, so using pH scale, and for that we have to dissolve it in water, no, sir?
Definitely, yes. By the moment you dissolve it in water, if it's a metal oxide, you're going to form a base, and that's the
Base.
reason why you're saying that the pH is less than 7. Sorry, greater than 7.
Arrhenius theory.
Arrhenius theory. Yes, absolutely. Yes. Okay. Right. Any other questions?
So why copper has 2 valencies, sir?
Why copper has 2 valencies? It is little beyond 10th class level, but I'll tell you, if you can understand, very good. If not, don't worry, you will anyway study it in 12th class. Okay. So what you have to understand is copper. If you look at the valence electron configuration will be 4. Oh, you don't know this, guys. No. Like, you don't know s orbital, p orbital, d orbital. You know only k shell, l shell, m shell, and all those, right? Do you know SPDF? Do you know you have any clue about it?
No, sir.
No, right? Don't leave it. You'll anyway study about it. Don't, right? Even if I tell you now, you'll not understand. Okay, copper has copper plus as well as copper 2 plus. It's possible. Yes, it's a very good question. Have this. Keep this in your mind. You will anyway study about this when I go for 11th class. You have to know. Basically, what we do is we write the shells in terms of K, L, M, N, and all that. But now, what we use in reality now is like not basically these are orbits, right? Each of these orbits will have s orbital, p orbital, d orbital, and stuff, right? The electronic configuration itself, you will not be writing it as 2, 8, 1 or something like that. You'll write 1s2, 2s2, something like that. You'll write. Don't worry about it. Do not worry about it, right? You will study them
So when
perfectly.
copper reacts with oxygen, sir, is it 2 oxide or 3 oxide, sir?
Depends. Generally, copper 2 oxide is more stable. Copper 2 plus is more stable than copper plus. So generally, you will form only Cu2O. Sorry, CuO is what is formed, right? But again, you will see Cu2O also getting formed, right? They're almost equally stable, right? But if you ask me copper plus or copper 2 plus, which is more stable in general, copper 2 plus is more stable.
Okay, sir.
Okay, right?
Yes.
Anyways, you'll study about all this. If you have really the, if you really want to learn, just learn it. Just Google it. Atomic orbitals, SPDF, something like that. You type, you'll get thousands of YouTube videos. Check it if you are interested.
Okay, sir.
Okay, fine. Any other questions, people? Okay, cool. That was a very nice interaction. You guys are very good. You guys are very good, like very much interacting. Almost all of you are very much interacting, right? So it's a very nice class. Thank you so much, people. We'll meet again next class. I'm going to end it. Thank you so much.
Thank you.
Thank you, sir.
Yeah.
Thank you, sir.
Thank you.
Thank you, sir.
Yeah.
Thank you, sir.
Yes. Thank you.